Good day, I'm Dr. T and welcome to my living room. So today I would like to talk about isotopic ratios and atomic weights. So in a previous video I had talked about atomic mass number. So we could take an isotope such as magnesium 24 and I can look at a periodic table. I check real quick that magnesium has 12 protons. And this is telling me that my mass number equals neutrons plus protons. And if this equals 24, and that equals something plus 12, then something must equal 12. Okay. Now, magnesium exists as three primary isotopes. Most of your elements will exist with a couple of different isotopes. For the most part, they're chemically pretty close to identical. There can be some subtle differences between them, mostly on their weight. Heavier atoms tend to move a little bit slower, and that does result in slightly different chemical reactivity. Now, with magnesium, of course, it has a couple of other isotopes. So I could have magnesium 25 and magnesium 26. And for this example, you'll see magnesium a lot because this has three dominant isotopes. A lot of elements will have one dominant isotope and a bunch of really little ones where they're fairly rare. But for magnesium, it's actually got three isotopes that are fairly reasonably abundant. And of course, I can do the same thing I did earlier. I could say 25 equals I don't know plus 12. Therefore, I don't know must equal 13. And 26 plus I don't know plus 12 or equals that. Therefore, I don't know must equal 13. Must equal 14. Yeah, so that's fairly straightforward. Now, when I look at these though, if I look on a periodic table, what I find is the mass of magnesium is 24.31 daltons. Daltons are a unit of mass. They are the mass of a proton in a carbon atom. You will also see these referred to as an atomic mass unit, which may be given the symbol AMU or U. The older AMU is definitely an obsolete unit. However, it still persists. Its definition is based off of oxygen. Okay, so yeah. Now, you would think that if I was to look at this, if I have three isotopes, then the average mass would be 25, wouldn't it? Because, you know, 1, 2, 3, I can average these, and, well, there's two things going on over here. For starters, when you have an isotope, instead of having the atomic mass number being the mass, that's only the case for carbon. The neutrons and protons actually change their mass depending on which nucleus they are in. They're closer to one neutron has a mass of 1 Dalton if it's in carbon, but they will deviate fairly significantly as you go away from carbon. And this is actually going to be coming back when we talk about nuclear chemistry. This is known as the mass defect, and this is the M in E equals mc squared. So let's actually look a couple of these up. So I've got off to the side a list. So magnesium 24, you'd think it has a mass of 24, but it's 23.985 Daltons. Okay, that's not much. So it's pretty close, but you know, we are looking at, if we want more than a couple of significant figures, this is actually going to have a small impact on us. Okay, and then magnesium 25 has a mass of 24.986 Daltons. And magnesium 26 has a mass of 25.983 Daltons. And all of these are rounded. They are known to more significant figures than what I'm showing. Okay, so, yeah, the mass should still be really close to 25, but when I look at a periodic table, it says it's 24.3. What's up? Well, if I'm to simply do a simple average of these, add the 3 up and then divide by 3, that's assuming that they're all equally abundant. There's as many magnesium 24s as there are 25s and 26s. However, if I actually go out into the wild and start looking for these, what I'll find is that 78.965% magnesium, the average, what you see on the periodic table, is actually going to be closer to it because in reality there's a fair amount more magnesium 24s. The other two isotopes are roughly similar in their abundance at 10.01% and at 11.03%. Okay. Now, you might be sitting there going, but wait, if I can't do a simple average, how do I calculate that information on the periodic table? Well, the approach that we're going to take is we use what's known as a weighted average. So in a weighted average, instead of assuming each one contributes equally, we apply a weighting factor. And in this case, the weighting factor is the percent abundance. So what I will do is I'll take these two numbers and I will multiply them together. Now, I have actually two choices. These are in percents. So when I have a percent, I can either multiply them straight out, and then I'll have 100 that I need to get rid of later, or I'll have to just get rid of the 100 to start with. Typically, I just get rid of the 100 to begin with. So let me grab my calculator, and I'm going to do 23.985 times 0.78965. Once again, I'm doing 0.78965 since this is a percentage, and I'm getting rid of that extra, 100% part of the equation. And this is going to equal 18.93975. And I am leaving way too many significant figures entirely intentionally. I will round later. Okay, next one, 24.986 times 0.1001 equals, this is going to be 2.5010986. Then the next one is going to be 25.983 times 0.1103 equals 2.865949. And in this case, it's actually helpful to look at where I would be putting my rounding if I was to do this. So 4 significant figures, that would be rounded there. 4 significant figures, that would be rounded there. I have 5 significant figures in that case, 5 in that case. So I would round 1, 2, 3, 4, 5, round there. Okay, so I'm going to round in that spot. Okay, so now what I end up doing is I add them all up together. So I will take 0.2865924 plus 2.5010986 plus 18.93975. Okay, and that gives me, I forgot a decimal point, didn't I? That number sounds a lot better. This gives me 24.30677, which once again I have to round to 3 places past the decimal point, so to that one. Therefore I get 24.307. And this would be in Daltons. These would all be in Daltons as well. Although once you're putting in the percent, things are getting a little bit weird. Yeah. So now I would look at a periodic table. My periodic table says 24.31 Daltons, which 24.31, this number rounds to that, so we're good to go. Now, you will see a couple of deviations when you look at periodic tables. The newest ones will quite often give you a range, and that is because these percentages aren't always fixed. The ones on your periodic table are typically given for just kind of the generic all over Earth. Obviously, things that are not on Earth won't necessarily have these same ratios of isotopes, and that is actually a way we can identify meteorites from just normal boring terrestrial rocks, because they will have ratios of assorted isotopes that don't match that which is typically found on Earth. However, there are quite a few elements where these ratios will actually vary a noticeable amount. And so when you look at them on the periodic table, instead of having one atomic weight, it will actually give you a range of atomic weights. In general, if you're using those atomic weights and you don't have any specific information, you just kind of pick a number in the middle of the range. It's probably going to be pretty close to what you're working with. But obviously, if you know that something is affecting that ratio and it will be at one end or the other of that range, then you would use whichever end you think you would end up having. So yeah, here are some atomic weights and calculating those from the abundance of isotopes. And with that said, have a wonderful day.